Welcome to Week 4 of Machine Learning Foundations. We'll begin the discussion in linear algebra, and in particular, we'll start with linear regression. In this lecture, we'll cover linear regression and also its close cousin, polynomial regression. The main idea we'll illustrate in this lecture is that solving a linear regression problem, which is essentially the same as solving a least squares problem, can be done directly by taking derivatives, giving you a set of equations. That system of equations turns out to be exactly the same system you get by using projections instead. We've already seen how to project onto the column space of a matrix A. We derived a set of equations you can solve even when the equation of times x equals b doesn't have an exact solution. We'll see that if we're given data points, say x1, y1, all the way up to xn, yn, and we want to do linear regression, the system of equations we get will be exactly the same as what we'd get using projections. We'll verify this by taking the calculus route in this class, taking derivatives of a certain sum of squares objective. And we'll follow that up with polynomial regression, which generalizes the curve fitting we saw in the previous week. Instead of fitting a straight line, you might fit something like a parabola, or a cubic polynomial, or another higher order curve, using a transformed set of features. That's what we'll look at in this lecture. So, welcome to this lecture on linear regression, something we've touched on before. So let's build on that understanding. We previously looked at the scalar version of this problem, but it generalizes to a d-dimensional parameter. Here's what we're given, data x1, y1, up through xn, yn, where each xi belongs to d-dimensional Euclidean space, and each yi is a real number, for I running from 1 to n. Given this, we define a loss function, and we're going to fit a linear function through this data. We want to minimize the sum of squared errors, the sum, from I equals 1 to n of the quantity xi transpose times theta minus yi squared. Now, how do we minimize this loss, L? We followed this recipe before, but let's repeat it to reinforce the idea. What we do is construct a matrix. To minimize L, define a matrix A by stacking all the feature vectors as rows, x1 transpose on top, down through xn transpose. Let's call this the feature matrix. Now, what is a times theta? It's the vector x1 transpose theta all the way down to xn transpose theta. We'll also define a vector using the letter y. Instead of calling it b, as we sometimes have in a general setting, let's use y here, since it fits our regression context better, y1 up through yn. So, times theta minus y gives us the vector x1 transpose theta minus y1 down through xn transpose theta minus yn. If we take this vector, a theta minus y transpose, and multiply it by itself, we get the sum, from I equals 1 to n, of the quantity xi transpose theta minus yi squared. So, L of theta is simply 1/2 times the quantity of theta minus y transpose times a theta minus y. Now we want to minimize this. Minimizing L is equivalent to setting the gradient of this function with respect to theta equal to 0. That means taking the gradient with respect to theta of a theta minus y transpose times a theta minus y, ignoring the constant factor of 1/2, and setting it equal to 0. This is equivalent to setting a transpose times the quantity of theta minus y equal to 0, which is the same as saying a transpose A times theta equals the transpose y. This is the same equation we've seen before. I'm just generalizing what we had in the scalar case. This is the least squares solution we've already encountered. Now, as I mentioned before, can we write theta as the inverse of a transpose A times a transpose y? The answer is yes, if it has full rank. Why? As an aside, if it has full rank, then a transpose is invertible. How do we argue this? I'll give you a hint, not the full solution. Show that the rank of A equals the rank of A transpose A. You can do this by showing that the null space of A equals the null space of A transpose A. By the rank nullity theorem, if two matrices have the same null space, they have the same rank. So if A has full rank, then a transposer also has full rank, and if a transposer has full rank, it's invertible. How do you show that the null space of A equals the null space of a transposer? That's a useful homework exercise. One direction is straightforward. For a hint, take some vector x that belongs to the null space of A, and show that x also belongs to the null space of a transpose A, and then work through the other direction as well. If you show both directions, you can conclude the two null spaces are identical, and therefore the two matrices have the same rank. So, if A has full rank, we can write the least squares regression solution in this particular closed form. Now, I'm going to jump ahead a little here to a connection you'll appreciate more fully later. In a later module on probability, we'll cover an important technique called maximum likelihood estimation. I won't define or explain it in full here, but I'll point out the connection now, and you can revisit this once you've learned both topics in more depth. Suppose the data is generated according to the following model. Imagine a linear model. If you pass in some x, the y you get out is theta transpose x plus some noise term, epsilon, which has zero mean. For example, say epsilon is Gaussian with mean 0 and some variance. Let's call it 1 over beta. Here, beta is typically referred to as the precision parameter, since precision is defined as the inverse of variance. To spell this out further, suppose you have a data set D consisting of pairs xi, yi, for I from 1 to n, generated independently in what's called an IID fashion, meaning independently and identically distributed. Each data point is sampled independently from the same distribution. Here, that distribution comes from our linear model, and they're all identically distributed. Given this setup, the maximum likelihood approach is to construct a function. Let's call it L of theta, which is the product of the individual densities. Since these are Gaussian densities, each term looks like e raised to the power of minus beta over 2 times the quantity yi minus theta transpose xi squared. Why this particular function? You'll understand that more fully later. This will be covered in the probability module. For now, let's just take it as a reasonable function to maximize. This maximum likelihood approach is to find a value of theta that maximizes L of theta. Now, instead of directly maximizing L of theta over theta, we can instead consider the log likelihood. This function, L of theta, is called the likelihood function, so we take its logarithm, log of L of theta. Since the logarithm is an increasing function, the optimal solution is the same whether we maximize L of theta directly or its logarithm. Why take the log at all? Simply because there's an exponential term involved, and it's much easier to differentiate once we've taken the log. So what does log of L of theta look like? It equals n over 2 times the log of beta plus n over 2 times the log of 2 pi. These two terms don't depend on theta at all. Plus a term that does depend on theta minus 1/2 times the sum over I of the quantity yi minus theta transpose xi squared. This remaining term, the one that depends on theta, is exactly the least squares objective we minimized earlier with respect to theta. So the key message is maximizing log of L of theta with respect to theta is the same as minimizing over theta, the least squares function. 1/2 times the sum over I of the quantity yi minus theta transpose xi squared. That's really the connection I wanted to make. When we perform least squares regression, we're effectively solving a maximum likelihood estimation problem. Or, put another way, least squares regression solves a maximum likelihood estimation problem under the assumption of a linear model with Gaussian noise. That's the message I wanted to convey here. You'll appreciate this connection much more fully once you understand why this likelihood function is written the way it is. That would be too much of a detail to cover properly within a linear algebra module, but you'll pick it up later. Whenever you learn about maximum likelihood estimation down the road, come back to this module and make the connection. The other topic I wanted to cover is polynomial regression. We were previously looking at curve fitting with a straight line. This is simply a generalization of that idea. Suppose we're again working with one-dimensional data, so our dataset consists of pairs xi, yi, for I from 1 to n, where both xi and yi are real numbers. Previously, we tried fitting a straight line through this data. Here, we generalize this to fitting any polynomial, say, of degree m. So you can fit an mth degree polynomial through the data. To do this, you consider what's called transformed features. If you want to fit a high-degree polynomial, given any x, instead of just theta 0 plus theta 1 times x, we write this more generally as the sum from j equals 0 to m of theta sub j times x raised to the power of j. So, for a given x, the transformed feature vector is simply 1 x squared all the way up to x raised to the power of m. Using this, we can write our prediction y hat of x as theta transpose times phi of x, where theta is the vector theta 0 through theta m, and phi of x is the transformed feature vector defined above. Now, using these transformed features, you perform ordinary linear regression, and that's exactly what polynomial regression is. Effectively, to repeat the earlier construction, instead of building the matrix using x1 transpose as the first row, you use phi of x1 transpose, and so on, down through phi of xn transpose. The vector y stays the same, y1 through yn, and then you solve the exact same system as before, a transpose A times theta equals a transpose y. The only difference here is that we're using transformed features. Compared to regular linear regression, the sole difference is that we transform the input features first and then perform regression as usual. The transformation shows up entirely in how we construct the matrix A. That's the whole trick behind polynomial regression. Now, the last topic before we close out this unit is a brief remark on a regularized version of linear regression. This is also known as rote regression. This will just be a quick note. The idea here is, instead of solving the minimization over theta of 1/2 times the sum from I equals 1 to n, the quantity xi transpose theta minus yi squared, we solve a regularized version instead. Let's call this regularized objective L bar theta, defined as the sum from I equals 1 to n, of the quantity xi transpose theta minus yi squared plus an additional term, lambda times the squared norm of theta. This extra term is the regularization term. What we do is minimize this new function, L bar of theta over theta, instead of minimizing the ordinary least squares objective. The advantage of this approach is, if you repeat the same derivation that led to our earlier least square solution, you can revisit the very first steps of this derivation. You end up with almost the same result, except instead of just a transpose A, you get a transpose A plus lambda times the identity matrix, set equal to the same right-hand side as before. So, theta equals the inverse of the quantity A transpose A plus lambda times the identity times A transpose Y. Here's another homework question I'll leave you with. Show that A transpose A plus lambda times the identity is invertible even when it does not have full rank. So, this is the regularized version and the parameter lambda. As you'll learn later, controls over fitting. This is something you'll explore in a much later course. Lambda is called the regularization parameter, and it controls overfitting. Too small a lambda can lead to significant overfitting, while too large a lambda leads to underfitting. This is just a forward-looking remark, not something we'll dig into in this course. One could explore the implications of lambda further in the context of the bias-variance trade-off, but that's outside the scope of this course. I'm just giving you a preview. With this, we conclude our discussion of least squares regression. Next, we'll move on to eigenvalues, eigenvectors, and matrix decompositions. To summarize what we covered in this lecture, first and foremost, we defined what a linear regression problem is. Given a set of data points, what does it mean to solve a linear regression problem? It simply means constructing a sum of squares objective and minimizing that objective over the input parameters. When we perform this minimization using calculus, taking partial derivatives and setting them to 0, the resulting system of equations turns out to be identical to the one we get by projecting onto the column space of the matrix. The second thing we covered was a bit of a forward reference, since you'll probably learn about maximum likelihood estimation later in the probability segment of the course, where you write down a likelihood function and maximize it with respect to some parameter. But to draw the connection to least squares now, we showed that if you write down a certain likelihood function, which will be explained more fully later, maximizing that function turns out to be equivalent to solving a least squares problem. That's the connection we established. And why this particular likelihood function makes sense is something you'll come to understand once we move into the probability portion of the course in a later week. The next thing we covered was polynomial regression, a generalization of the line fitting we saw in the previous week. Instead of fitting a straight line, you can fit a higher degree polynomial and still perform linear regression by transforming your input features into higher dimensional quantities. For example, to fit a parabola, a cubic polynomial, or any higher order polynomial. How do we do this? The idea is simple. Just as with ordinary linear regression, polynomial regression also comes down to solving a system of equations very closely related to the one we get from projecting onto a column space in the straight line fitting case. That's what we worked through here. Then, as a forward-looking remark, we saw that a system of equations used to solve either polynomial regression or ordinary linear regression can be modified by adding a regularization parameter, something with deep machine learning significance that you'll explore in a future course. From a purely linear algebra standpoint, though, this regularization ensures that a certain matrix becomes invertible, letting you solve the system directly by inverting that matrix and multiplying it by another vector, something that isn't always guaranteed in the unregularized, projection-based system of equations. So you can introduce a regularization parameter to resolve this invertibility issue. But this parameter also carries a much deeper significance. It helps manage the balance between underfitting and overfitting, or what's called the bias variance trade-off. That's a topic for a follow-up course. Not this one, but you'll certainly encounter it down the road.
Welcome to yet another lecture of the Machine Learning Foundations course. We're in week 4, and this is the second lecture. We'll begin the discussion with some core linear algebra concepts. In particular, the most important concept here is the eigenvalue, along with something closely associated with it, the eigenvector. We're going to understand eigenvalues and eigenvectors for a given matrix. We'll start with a brief motivation that illustrates why we need this concept in the first place. Then we'll concretely define, for a given matrix, what an eigenvalue is and what an eigenvector is. After that, we'll look at a systematic procedure for calculating all the eigenvalues and eigenvectors of a given matrix. We'll start with eigenvalues and eigenvectors, and then build on this to cover several related topics: real symmetric matrices, eigenvalue decomposition, and as a further step, singular value decomposition. Finally, we'll end with principal component analysis. That's the plan for this module, the third linear algebra module. Let's begin with the basics. What are eigenvalues and eigenvectors? Before I define them, let's start with some motivation for why we care about them at all. The motivation I'll use comes from ordinary differential equations. Imagine you have an equation like this. The derivative of v with respect to t equals 4 times v minus 5 times w with the initial condition v equals 8, at t equals 0. And the second equation, the derivative of w with respect to t equals 2 times v minus 3 times w with the initial condition w equals 5 at t equals 0. Let's write this more compactly. Think of v and w together as a single vector, u, a two-dimensional parameter, with u at time 0 equal to the pair 8 and 5. Given this, we can rewrite our system of equations. Let's call it star, as the derivative of u with respect to t equals a times u, where is the coefficient matrix 4 minus 5 in the first row, 2 minus 3 in the second row, with the initial condition given at t equals 0. Now, solving an ordinary differential equation like this naturally leads us to eigenvalues and eigenvectors. Let's look at a very simple case first. Just a single equation. Suppose we just have the derivative of u with respect to t equals a times u, where is now just a single number. The solution to this is u of t equals e raised to the power of a times t times u at time 0. You can substitute this back in and check that it satisfies the equation. Let's call this equation double star. It's easy to verify this is indeed a solution. Now, one is often concerned with the stability of such solutions. This goes a bit beyond the scope of this course, but people generally care about stability here. The system is unstable if it is greater than 0, simply because e raised to the power of a t grows to infinity as t increases. It's called neutrally stable in a certain boundary case. Not something we need for this course. And the third, most interesting case, it's stable if it is less than 0, because the solution decays toward a constant value, since e raised to the power of a t shrinks towards 0. Now let's look at the two-dimensional case. Suppose we want solutions of a particular form, v of t equals e raised to the power of minus lambda times t times y, and w of t follows a similar form for the system star that we outlined earlier. Or, writing it in vector form, we want u of t to equal e raised to the power of minus lambda times t times x, where x is the vector consisting of y and z. If we substitute this into our equation, the derivative of u with respect to t equals a times u, we get, plugging into our two original equations, minus lambda times e raised to minus lambda t times y equals 4 times e raised to minus lambda t times y plus 5 times e raised to minus lambda t times z. And a similar equation involving v and w. If we factor out e raised to the power of minus lambda t from both sides, we arrive at a very important equation. This equation turns out to be exactly the same as a times x equals lambda times x. This is the eigenvalue equation. In other words, solving a linear system within an ordinary differential equation ultimately comes down to solving this eigenvalue equation, where lambda is called the eigenvalue, and we want a non-trivial eigenvector, x. Meaning x should not simply be the 0 vector. So the message is, we can solve the equation, the derivative of u with respect to t equals a times u, using solutions of the form u of t equals e raised to the power of minus lambda t times x, provided we can solve a times x equals lambda times x. That's really the key message, and it leads naturally to the definitions of eigenvalues and eigenvectors. To summarize, solving a linear system of ordinary differential equations is really tied to solving an eigenvalue equation. If we can solve that eigenvalue equation, we can construct a solution of the exact form described, provided we can find a non-trivial x satisfying a times x equals lambda times x. So, here's the formal definition. For a matrix A, lambda is called an eigenvalue and x is called an eigenvector if a times x equals lambda times x. This is called the eigenvalue equation. Geometrically, if x is some vector, then a times x either stretches x or shrinks it. But crucially, it never changes the direction of x. That's the definition of an eigenvalue, an eigenvector. Let's look at a special case. If lambda equals 0, then a times x equals 0, which means x must belong to the null space of A. That's the simplest possible example. Now let's look at a few more examples where you can find the eigenvalues and even the eigenvectors just by inspection. The first example is a projection matrix, something we saw in the previous module. Let's call this matrix P. For example, imagine projecting vectors onto a plane. Take any vector, x, and P times x lands somewhere in that plane, forming a right angle with the difference between x and its projection. I'd recommend pausing here and thinking about the eigenvalues and eigenvectors of this projection matrix yourself before I give the answer. Try to reason through the possible eigenvalues and eigenvectors in this simple case. Here's the answer. For any x that already lies in the plane, P times x simply equals x. This means lambda equals 1 is an eigenvalue, and any vector lying within the plane is a corresponding eigenvector. What about a second eigenvalue? Yes, there is one. Consider a vector, x, that's perpendicular to the plane. What happens to P times x in that case? If x is already perpendicular to the plane, projecting it onto the plane gives exactly 0. So lambda equals 0 is another eigenvalue, and any vector perpendicular to the plane is a corresponding eigenvector. That's our first example. Let's look at another example. A permutation matrix. By definition, a permutation matrix is formed by taking the identity matrix and shuffling its rows. For example, the 2 by 2 matrix with 0 and 1 in the first row and 1 and 0 in the second row is a permutation matrix. Pause and try to work out its eigenvalues and eigenvectors yourself. I'll give you one example. Try to find an x such that P times x equals x. The answer is x equal to the vector 1, 1. For the second eigenvector, try to find an x such that P times x equals minus x. I've already told you the eigenvalue is minus 1, so try to figure out the eigenvector. The answer is x equal to the vector 1, minus 1. So, for these very simple matrices, you can often just eyeball them and guess the eigenvalues and eigenvectors. But there's a more systematic procedure for finding them in general. Let's start with the eigenvalue equation. A times x equals lambda times x, which is equivalent to saying the quantity of minus lambda times the identity matrix times x equals 0. This is equivalent to saying that the matrix of minus lambda times the identity is singular, meaning it doesn't have full rank, which finally leads us to the equation. The determinant of a minus lambda times the identity equals 0. This particular equation is called the characteristic polynomial of the matrix A. If there's an n by m matrix, then the characteristic polynomial has degree n. You can write it out as a polynomial in lambda, built from the diagonal entries. Something like the quantity a11 minus lambda times the quantity ann minus lambda, and so on, set equal to 0. That's the general shape of the characteristic polynomial. The n roots of this polynomial equation are exactly the eigenvalues of the matrix. That's how you find them. Now, that answers one part of the problem. Finding the eigenvalues. How do you find the corresponding eigenvector? We saw that we're looking for an x such that a minus lambda times the identity times x equals 0. So, for eigenvectors, given a particular eigenvalue, lambda, we want x to satisfy this equation. Meaning x must belong to the null space of the matrix a minus lambda times the identity. Finding this null space gives you the eigenvector corresponding to that eigenvalue, lambda. That's really the overall scene, and you can use Gaussian elimination to solve the equation. A minus lambda times the identity times x equals 0. Let's work through an example. Suppose there's the 2 by 2 matrix, 3, 1 in the first row, 1, 3 in the second row. I'd recommend pausing the video, calculating the eigenvalues and eigenvectors yourself, and then checking against the lecture to see if you got it right. If we compute the determinant of a minus lambda times the identity and set it to 0, we get lambda squared minus 6 lambda plus 8 equals 0. This tells us that the sum of the two eigenvalues, lambda 1 plus lambda 2, equals 6, and their product equals 8. You can verify that the sum of the eigenvalues equals what's called the trace of A, the sum of its diagonal entries, and the product of the eigenvalues equals the determinant of A. In this case, 3 plus 3 gives 6, matching the diagonal sum, which equals the sum of the two eigenvalues, and so on. Solving this, the eigenvalues turn out to be lambda 1 equals 4 and lambda 2 equals 2. Now let's find the corresponding eigenvectors. Look at a minus 4 times the identity. Subtracting 4 from each diagonal entry gives us the matrix minus 1, 1 in the first row, 1, minus 1 in the second row. We want to find a vector x such that this matrix multiplied by x gives 0. You can check that x equal to the vector 1, 1 satisfies this. And so does any scalar multiple, like the vector 2, 2, and so on. For the other eigenvector, look at a minus 2 times the identity, which gives 1, 1 in the first row, 1, 1 in the second row. We want x such that this matrix times x equals 0. This time, the vector 1, minus 1 works. So that was a simple example where the eigenvectors were easy to find directly. Here's a variation on this matrix. Suppose we construct a matrix B closely related to A. Say the matrix with 0, 1 in the first row and 1, 0 in the second row. How is B related to A? It turns out that B plus 3 times the identity equals A. So what does A times x look like in terms of B? It equals B times x plus 3 times x, which is B's eigenvalue plus 3 times x. Here's a homework question for you. Think about why the eigenvectors of B are exactly the same as the eigenvectors of A. Try to argue this yourself. Let's end with a few important remarks. You have to be careful when reasoning about eigenvalues in combination. Suppose we have two matrices and B, where times x equals lambda 1 times x and B times x equals lambda 2 times x. Can we then claim that the matrix A plus B times x equals the sum lambda 1 plus lambda 2 times x? Pause and think about this. Can we really claim that if A has eigenvalue lambda 1 and B has eigenvalue lambda 2, then A plus B has eigenvalue lambda 1 plus lambda 2, using the same eigenvector x for all three? Unfortunately, the answer is no, because the eigenvector for A and the eigenvector for B need not be the same vector at all. You might have A times x1 equals lambda 1 times x1, and B times x2 equals lambda 2 times x2, where x1 and x2 are not necessarily equal. In fact, we will return to this point later, toward the end of our discussion on eigenvalue decomposition, coming up soon. One important fact, if you have a symmetric matrix, its eigenvalues are guaranteed to be real numbers. To really appreciate why this matters, it helps to see an example of a matrix whose eigenvalues are not real. Here's such a matrix. Pause again and think about an example yourself before I give the answer. There are many possible examples. Here's the simplest one, the 2 by 2 matrix with 0, minus 1 in the first row and 1, 0 in the second row. If you compute the determinant of A minus lambda times the identity, you get lambda squared plus 1 set to 0. Meaning the eigenvalues turn out to be the imaginary numbers I and minus I. Also, in an earlier example, we found two eigenvectors that turned out to be linearly independent of each other. This doesn't always happen. Let me give you an example of a matrix where it fails, where we don't get two independent eigenvectors. Consider the matrix 3, 1 in the first row, 0, 3 in the second row. You can see fairly easily that both eigenvalues equal 3. Lambda 1 equals lambda 2 equals 3. Now a minus lambda times the identity becomes 0, 1 in the first row, 0, 0 in the second row. The only non-trivial eigenvector here is the vector 1, 0. And there's no other eigenvector linearly independent from it. So, for this 2 by 2 matrix, we only get a single independent eigenvector, even though there are 2 eigenvalues. Let's do a quick summary before we wrap up this lecture. In this lecture, we looked at the motivation for using eigenvalues and eigenvectors, specifically how they help us understand the solutions to ordinary differential equations. We worked through a concrete example, and then, after formally defining eigenvalues and eigenvectors, we saw that computing eigenvalues comes down to solving what's called the characteristic polynomial, derived from setting the determinant of a minus lambda times the identity equal to 0. We also connected this to the trace and the determinant of a matrix in relation to its eigenvalues. In the next lecture, we'll look at how many linearly independent eigenvectors we can find for a given matrix, and whether having enough of them allows us to diagonalize the matrix. This idea of diagonalization is closely tied to how many linearly independent eigenvectors a matrix has. If a matrix is n by n, and we can find n linearly independent eigenvectors, then that matrix is diagonalizable. This is an important idea that we'll build on in the next lecture. Welcome to lecture number 3 in week 4 of Machine Learning Foundations. In this lecture, we'll start the discussion about similarity and diagonalization of a matrix. In particular, we'll define what it means to say that a matrix A is diagonalizable and relate this to the idea of linear independence among the eigenvectors of that matrix. Whether a matrix is diagonalizable is strongly tied to how many linearly independent eigenvectors we can find. Specifically, whether we can find enough of them to diagonalize the matrix. We'll also look at a special case. If you have an n by n matrix, all of its eigenvalues happen to be distinct, then it's automatically diagonalizable because you're guaranteed to get enough independent eigenvectors. That's a particularly interesting special case we'll cover. In the lectures that follow, we'll build up this theory toward our final destination, the spectral theorem, which tells us that any real symmetric matrix is diagonalizable. We'll get there step by step. That's the goal we're heading toward. So, we'll come back to this linear algebra module. In the previous lecture, we covered eigenvalues and eigenvectors, motivated by ordinary differential equations. Today, we'll look at a very important related topic, similarity and diagonalization of matrices. So, what is a diagonalizable matrix? Let's start with the definition. A matrix A is diagonalizable if there exists an invertible matrix S, such that S inverse times A times S gives you a diagonal matrix. In other words, if we can find an invertible matrix S such that S inverse S equals some diagonal matrix. Let's call it capital lambda. Then A is diagonalizable. Let's dig into this further. When is a matrix diagonalizable? It really comes down to having enough independent eigenvectors. Let's make this precise. Suppose it's an n by n matrix with n linearly independent eigenvectors. Call them x1 through xn. Then A is diagonalizable. Why is that true? To show diagonalizability, we need to construct an invertible matrix S, such that S inverse S is diagonal. Here's how we do it. Let S be the matrix formed by taking all of these eigenvectors and placing them as the columns of S. Now, the question is S invertible? Pause and think about this yourself. What's the rank of S? The rank of S is n, because x1 through xn form a linearly independent set. A linearly independent set of n vectors in n-dimensional space automatically has full column rank. Now, what is a times S? A times S equals a times x1 through a times xn. But these aren't just any vectors, they are the eigenvectors of a specifically. So, a times x1 equals lambda 1 times x1, and so on, where lambda 1 is the eigenvalue corresponding to eigenvector x1, and so forth, up through lambda n and xn. We can rewrite this as the matrix formed by x1 through xn multiplied by a diagonal matrix containing the eigenvalues, which is exactly S multiplied by that same diagonal matrix. So, A times S equals S multiplied by the diagonal matrix of eigenvalues. That's enough to establish diagonalizability, since this is equivalent to saying S inverse times A times S equals the diagonal matrix. And we've already shown S is invertible. So the key point is, a matrix is diagonalizable if it has enough independent eigenvectors. Here's a useful special case. Suppose lambda1 and lambda2 are eigenvalues, with corresponding eigenvectors x1 and x2, and suppose lambda1 and lambda2 are distinct. That is, lambda1 does not equal lambda2. Then x1 and x2 form a linearly independent set. In other words, eigenvectors corresponding to different eigenvalues are automatically linearly independent from each other. Let's prove this. We start with the linear independence condition. Suppose some constant c1 times x1 plus another constant c2 times x2 equals 0. Call this equation 1. If we apply to both sides, the right side stays 0, since the times 0 is 0. But the left side becomes c1 times the times x1 plus c2 times the times x2, which is c1 times lambda1 times x1 plus c2 times lambda2 times x2. Call this equation 2. If we subtract equation 1, appropriately scaled, from equation 2, we get c1 times the quantity lambda1 minus lambda2 times x1 equals 0. Since lambda1 does not equal lambda2 and x1 is not the zero vector, the only way this equation can hold is if c1 equals 0. By a similar argument, c2 must also equal 0. This means x1 and x2 are indeed linearly independent. This result extends naturally. I won't prove the general case here, but the same argument applies. If lambda1 through lambda n are all distinct, then their corresponding eigenvectors x1 through xn are linearly independent. I'll leave the general proof as a homework exercise. Just follow the same reasoning we used above. Let's work through an example. Take the matrix A with rows 1, 4, and 2, 3. Let's calculate its eigenvalues and eigenvectors for practice. The matrix A minus lambda times the identity has diagonal entries 1 minus lambda and 3 minus lambda with 4 and 2 off the diagonal. Setting up the characteristic equation, I'd recommend pausing here and working this out yourself before checking against what I get. The roots turn out to be lambda1 equals 5 and lambda2 equals minus 1. So, is it diagonalizable? Yes! Because it has two distinct eigenvalues, its corresponding eigenvectors automatically form a linearly independent set, giving us enough independent eigenvectors to diagonalize the matrix. Now we need to find those eigenvectors. Let's start with lambda equals 5. The corresponding matrix, a minus lambda1 times the identity, works out to have minus 4 and minus 2 along one structure with matching off-diagonal entries. What's the null space of this matrix? If you look at the columns, adding them together gives 0. So that tells us the eigenvector x1 equals the vector 1, 1. Now let's look at the second eigenvalue, lambda2 equals minus 1. In this case, a minus lambda2 times the identity works out to have rows of 2, 4, and 2, 4. To find a combination of columns that gives 0, you can take minus 2 times the first column plus 1 times the second column, giving us x2 equals the vector minus 2, 1. That's it. Now we can form our matrices. The matrix S is formed by stacking the eigenvectors as columns 1, 1 in the first and minus 2, 1 in the second. The diagonal matrix contains the eigenvalues 5 and minus 1. Just be careful to list the eigenvalues in the same order as their corresponding eigenvectors in S. You can then verify that S inverse times A times S equals this diagonal matrix. Plugging in the numbers, S inverse times the matrix 1, 4, 2, 3 times S gives exactly the diagonal matrix with 5 and minus 1 on the diagonal. That's a complete word example. I'd encourage you to try a few more problems yourself. Maybe even a slightly higher dimensional case, like a 3 by 3 matrix, and practice diagonalizing it. Let's continue with a few remarks and observations. First remark, is the matrix S unique for a given matrix? Think about this yourself. The answer is no. Why? If x1 is an eigenvector, then any non-zero scalar multiple of x1 is also a valid eigenvector. So, in the previous example, instead of using the vector 1, we could just as easily have used 2, 2, and still gotten a perfectly valid S. So, the columns of S can be rescaled to produce a different matrix, S' and S' inverse times A times S' will still be a diagonal matrix. The diagonal matrix itself won't change. Its centers are always the eigenvalues of A, which are fixed, but the specific matrix of eigenvectors can vary. Here's a related, more precise second remark. Suppose it can be written as S times the diagonal matrix times S inverse. Call this decomposition setup. Suppose the first column of S is some vector, y. What's the first column of S times the diagonal matrix? By definition, it's simply lambda 1 times y. And what's the first column of a times S? That's just applied to the first column of S, which is a times y. Since a times S equals S times the diagonal matrix, this means a times y equals lambda 1 times y, which tells us that lambda 1 is indeed an eigenvalue of A, and y is a corresponding eigenvector. So the point here is, if it is diagonalizable, the diagonal matrix can only ever contain the eigenvalues of A, and the matrix S must contain corresponding eigenvectors of A. The matrix S itself isn't unique, but there's only ever one set of eigenvalues for a given matrix. So the diagonal matrix itself is always the same, regardless of which valid S you choose. Let's look at another remark, this time about powers of A. Suppose lambda is an eigenvalue and x is a corresponding eigenvector of A. What can we say about a squared times x? Well, a squared times x is just applied to a times x. And since x is an eigenvector, a times x equals lambda times x. So a squared times x equals applied to lambda times x, which equals lambda times a times x, which equals lambda times x. In other words, lambda squared times x. Now, suppose S inverse times A times S is a diagonal matrix. What about S inverse times a squared times S? Does equal the diagonal matrix squared? Think about this yourself, given what we've already established. Essentially, can we use the same matrix of eigenvectors to diagonalize a squared? The answer is yes. Why? It's easy to see. If you take S inverse S and multiply it by S inverse S again, you get S inverse times a squared times S on the left and the diagonal matrix squared on the right. And there's nothing special about squaring specifically. This same argument works for any positive integer power, k. So you can infer that S inverse times e to the power of k times S equals the diagonal matrix raised to the power of k. Now, one final remark. As an example of a matrix that fails to have enough independent eigenvectors, consider a matrix where you can check directly that it doesn't have two linearly independent eigenvectors. You can verify this by calculating its eigenvalues, which turn out to be straightforward, and then calculating the corresponding eigenvectors. You'll find you only get a single independent eigenvector, even though the matrix is two-dimensional. Let's recap before we end this lecture. What we learned today, we covered the concept of diagonalizing the matrix. Diagonalization involves two matrices. The first is the matrix whose columns have the eigenvectors, and this matrix needs to be invertible. The second is a diagonal matrix containing the eigenvalues along its diagonal. An n by n matrix is diagonalizable if and only if you can find n linearly independent eigenvectors for it. Otherwise, it isn't diagonalizable. We looked at two simple examples, including a 2 by 2 matrix where we found two linearly independent eigenvectors, and we directly computed its diagonalized form, writing out the full decomposition to demonstrate diagonalizability. In the lectures that follow, we'll dig deeper into which matrices are diagonalizable and which aren't. In fact, the central result we're building toward is the spectral theorem, which shows that any real symmetric matrix is always diagonalizable. Welcome to another lecture in week 4 of Machine Learning Foundations. We'll continue our discussion of linear algebra and in particular, look at a concrete example that shows off the usefulness of diagonalization, the well-known Fibonacci sequence. Suppose you want to calculate a higher order term in the Fibonacci sequence without brute forcing it term by term. If you're okay with a good approximation, you can use linear algebra. Specifically, ideas from diagonalization to figure out what these higher order Fibonacci terms look like. That's exactly what we're going to do in this lecture. We'll continue our discussion of similarity and diagonalization through this detailed example, the Fibonacci sequence. I'm hoping everyone's familiar with it. Linear algebra will let us answer some interesting questions about it. As a reminder, the sequence starts with 0 and 1, and each subsequent number is the sum of the previous two, 0, 1, 1, 2, 3, 5, and so on. 2 plus 1 is 3, 3 plus 2 is 5, and so forth. That's the Fibonacci sequence. If we write this as a recurrence relation, let's denote the sequence as f sub k. Then f sub k plus 2 equals the sum of the previous two terms, f sub k plus 1 plus f sub k. Now, our question is, suppose we want to know what f100 is. We could compute this manually or let a computer grind through it, but these kinds of questions can be answered much more elegantly using linear algebra. The linear algebra solution to this uses diagonalization. To get started, we need a matrix. Let's write down a system of equations. F sub k plus 2 equals f sub k plus 1 plus f sub k. And let's add a second, trivial equation, f sub k plus 1 stays unchanged, equal to itself. Now, if we track how this pair evolves, call it a vector, u sub k, and want to write u sub k plus 1 as some matrix times u sub k, what would that matrix look like? Think about this yourself. The answer is, if we write the pair, f sub k plus 2, f sub k plus 1, this equals the 2 by 2 matrix with rows 1, 1, and 1, 0, multiplied by the pair, f sub k plus 1, f sub k. Working through the matrix multiplication, you get f sub k plus 1 plus f sub k in the first entry, and f sub k plus 1 in the second entry, exactly matching the system of equations we started with. So, let's call this matrix the 2 by 2 matrix with rows 1, 1, and 1, 0. We start with an initial vector, u at iteration 0, equal to the pair 0, 1, actually the first two Fibonacci numbers, and then keep applying it repeatedly. Apply it once to get u1, apply it again to get u2, apply it again for u3, and so on. So, in general, u at iteration k equals applied k times to the initial vector, u at iteration 0. And this is exactly the solution to the recurrence, u sub k plus 1 equals a times u sub k. Now, how do we actually compute u sub k? Here's a general idea, applicable beyond just the Fibonacci case. Suppose you have a similar system where it's an n by m matrix, and each u sub k is an n-dimensional vector. If it is diagonalizable, meaning it has n linearly independent eigenvectors. Then we can proceed as follows. Start with the initial vector u at iteration 0. Since the eigenvectors x1 through xn form a basis for the space, we can write u at iteration 0 as some linear combination of these eigenvectors. Say c1 times x1 plus c2 times x2, and so on, up through cn times xn. Now, if we apply to this combination, we get c1 times a times x1 plus c2 times a times x2, and so on. But since each xi is an eigenvector, a times xi is just lambda I times xi. So this becomes c1 times lambda 1 times x1 plus c2 times lambda 2 times x2, and so on, through cn times lambda n times xn. What is u at iteration k? It's just a applied k times to u at iteration 0. If we apply once more, what happens? A squared times u at iteration 0 becomes applied to the expression c1, lambda 1 x1 plus the rest, which works out to c1 times lambda 1 squared times x1 plus c2 times lambda 2 squared times x2, and so on. Extending this logic further, in general, u at iteration k equals c1 times lambda 1 raised to the power of k times x1 plus c2 times lambda 2 raised to the power of k times x2 all the way through cn times lambda n raised to the power of k times xn. Now let's bring this back to Fibonacci. To find u sub k, we need to check whether the matrix with rows 1, 1 and 1, 0 is diagonalizable, and if so, find its eigenvectors. So, what is a? It's the matrix 1, 1, 1, 0. Pause the video now and calculate this yourself. The characteristic equation turns out to be lambda squared minus lambda minus 1 equals 0. Solving this quadratic gives us lambda 1 equals 1 plus the square root of 5, all divided by 2, and lambda 2 equals 1 minus the square root of 5, all divided by 2. This is just high school algebra, solving the quadratic equation. We start with u at iteration 0, which is the pair f1, f0. The first two Fibonacci numbers, 1 and 0. We want to write this as c1 times x1 plus c2 times x2, where x1 and x2 were the eigenvectors. So let's find those eigenvectors. What is a minus lambda times the identity? It's the matrix with entries 1 minus lambda, 1, 1, 1 minus lambda. We want to find x such that this matrix times x equals 0. Let's guess x1 equals the pair lambda 1, 1, and x2 equals the pair lambda 2, 1. Let's check a minus lambda 1 times the identity times the pair lambda 1, 1. This works out to lambda 1 squared minus lambda 1 minus 1 in the first entry. But recall the characteristic polynomial. Lambda 1 satisfies lambda squared minus lambda minus 1 equals 0. So this entry is exactly 0, since lambda 1 is a root of that equation. Similarly, a minus lambda 2 times the identity times the pair lambda 2, 1 also gives 0. So x1 and x2 are indeed the eigenvectors corresponding to lambda 1 and lambda 2. Now that we have this basis, we can write u at iteration 0 as a linear combination of x1 and x2. Let's do that. We want u at iteration 0. The pair 1, 0, the first two Fibonacci numbers, to equal some constant times the pair lambda 1, 1, where lambda 1 equals 1 plus the square root of 5 over 2, plus another constant times the pair lambda 2, 1, where lambda 2 equals 1 minus the square root of 5 over 2. Working backward, you can solve for these constants directly. If you check the algebra, the first constant turns out to be 1 over the square root of 5, and the second constant is minus 1 over the square root of 5. If you substitute these in, The second components just cancel out to give 1, and the first components combine to give 0, as expected, once you carefully add everything up. So, what is u at iteration k? It's c1 times lambda 1 raised to the power of k times x1 plus c2 times lambda 2 raised to the power of k times x2. Exactly as we derived before. This gives us the pair f sub k plus 1 f sub k. In particular, focusing on f sub k itself, it equals 1 over the square root of 5 times the quantity 1 plus the square root of 5 over 2, all raised to the power of k, minus 1 over the square root of 5 times the quantity 1 minus the square root of 5 over 2, all raised to the power of k. You can verify that the second term, involving 1 minus the square root of 5 over 2, has a magnitude less than 1. So, as k grows large, its second term shrinks towards 0 and becomes negligible. This gives us a very good approximation. F sub k is approximately just the first term. 1 over the square root of 5 times the quantity 1 plus the square root of 5 over 2 raised to the power of k. So, for example, if you want the 100th Fibonacci number, you can approximate it as 1 over the square root of 5 times the quantity 1 plus the square root of 5 over 2 raised to the power of 100. Numerically, that inner quantity works out to about 1.618, so you're essentially computing 1 over the square root of 5 times 1.618 raised to the 100th power. That gives you the 100th Fibonacci number, to a very good approximation. So, the takeaway from this application is that diagonalizability lets us understand interesting properties of linear recurrence relations. The key requirement is that the recurrence has to be linear. What do I mean by that? Going back to our equation, u sub k plus 1 is some linear function of u sub k. If instead this relationship were nonlinear, this entire approach would break down. This technique works precisely because we have a linear recurrence relation, letting us bring in tools from linear algebra, like diagonalizability, to understand what happens to the sequence after a large number of iterations. Let's do a quick recap before ending this lecture. In this lecture, we worked through a concrete example illustrating the usefulness of diagonalization. Specifically, how diagonalizing a matrix can help solve a linear recurrence relation. We used the well-known Fibonacci sequence as our example, since it's clearly a linear recurrence relation. We set up the recurrence in matrix form and diagonalized the underlying 2 by 2 matrix. Using this diagonalized form, we found the eigenvalues and eigenvectors, which let us derive a very good approximation for higher-order Fibonacci terms. For example, we saw how to compute the 100th Fibonacci number without any brute force, step-by-step calculation, just by diagonalizing a matrix, finding its eigenvalues and eigenvectors, and using that information directly. This approach is far less computationally intensive than calculating the sequence term by term, and the same idea generalizes to solving linear recurrence relations more broadly. Whenever you need to solve a linear recurrence, diagonalization is an extremely useful tool. In the lectures that follow, we'll move toward the spectral theorem, which shows that any real symmetric matrix is diagonalizable and that all of its eigenvalues are real. A real symmetric matrix always has only real eigenvalues. This important result, the spectral theorem, is what we'll be building toward over the next few lectures.
Welcome to the last lecture in week 4 of Machine Learning Foundations. In this lecture, we'll state the spectral theorem for the real case, and we'll apply this theorem to diagonalize a simple 2 by 2 matrix. As I've mentioned in previous lectures, the main idea behind the spectral theorem is that it guarantees diagonalizability for a particularly important class of matrices, real symmetric matrices. Specifically, it says that any real symmetric matrix is diagonalizable, and more than that, it's orthogonally diagonalizable. We'll unpack exactly what that means. For now, we'll take this as a given fact, and in later lectures, we'll
actually prove it in a more general setting involving complex vector spaces, where the natural generalization of a real symmetric matrix is what's called a Hermitian matrix. We'll prove the spectral theorem in that more general setting later. But in this lecture, we'll focus on the real case, work through an example, and see how to orthogonally diagonalize a matrix. From here, we'll spend the next few lectures building toward the following main result about diagonalizing real symmetric matrices. Here's the result. Suppose it is a real symmetric matrix. Then the following facts about it are all true. First, the eigenvalues of it are real numbers. Second, eigenvectors corresponding to different eigenvalues are linearly independent. And third, by far the most important fact, it is orthogonally diagonalizable. This third point is a stronger version of the usual diagonalizability claim. What does orthogonal diagonalizability mean? It means there exists a matrix, Q, satisfying a particular property. Such a matrix is called an orthogonal matrix, such that it can be written as Q times the diagonal matrix of eigenvalues times Q transpose. In other words, if you build Q by stacking the eigenvectors x1 through xn as columns, then it equals Q times the diagonal matrix containing the eigenvalues times Q transpose, where Q transpose is just the matrix with those same eigenvectors as rows instead of columns. This holds for any real symmetric M by N matrix. One small but important fact, this orthogonality property implies that Q inverse equals Q transpose. So, what we have is diagonalizable in the usual sense, but with the added bonus that the matrix used for diagonalization is orthogonal. That's what orthogonally diagonalizable means. It's the same as saying it equals Q times the diagonal matrix times Q inverse, but where Q transpose times Q equals the identity matrix, which lets us write it as Q times the diagonal matrix times Q transpose directly. This is the major result. We haven't proven it yet, but we will, after covering some necessary background. For now, take it as a fact you can rely on. If your matrix is real and symmetric, it's guaranteed to be diagonalizable in this stronger, orthogonal sense. The key requirement is that the matrix needs to be both real and symmetric. Not every real matrix is diagonalizable. We've already seen an example of this in an earlier lecture. So, remark 1, a real matrix isn't necessarily diagonalizable in general. But a real symmetric matrix is always diagonalizable. And moreover, we can always find an orthogonal matrix to diagonalize it. We already saw, in a previous lecture, an example of a matrix that isn't diagonalizable at all. For reference, that non-diagonalizable example was definitely not symmetric. Let's work through an example to understand orthogonal diagonalizability concretely. Take the matrix A with rows 1, -2, and -2, -2. Pause the video and work through the calculations yourself. I'll just give you the main results. The eigenvalues turn out to be λ1 equals -3 and λ2 equals 2. The corresponding eigenvectors, I'll call them x1 and x2 before normalizing them, are x1 equal to the pair 1, 2 and x2 equal to the pair -2, 1. Now, let's normalize these to get orthonormal vectors. Define q1 as x1 divided by the length of x1. The length of x1 is the square root of 1 squared plus 2 squared, which is the square root of 5. So q1 becomes 1 over the square root of 5 times the pair 1, 2. Similarly, q2 is x2 divided by its length, which also turns out to be the square root of 5. Giving q2 as 1 over the square root of 5 times the pair -2, 1. Now we build the matrix Q by placing q1 and q2 as its columns, 1 over the square root of 5, and -2 over the square root of 5 in the first row, 2 over the square root of 5, and 1 over the square root of 5 in the second row. You can check that Q transpose times Q gives the identity matrix. This is an important sanity check to perform whenever you construct an orthogonal matrix, whether you're working through homework or an exam problem. Now, What is Q times the diagonal matrix of eigenvalues times Q transpose? Working through the matrix multiplication, with the diagonal matrix containing -3 and 2 along the diagonal, and Q transpose being the transpose of Q, you'll find this product works out to exactly the original matrix, 1, -2, -2, -2. So, that's a complete example. The important takeaways: I could certainly diagonalize using the original, unnormalized eigenvectors x1 and x2. But if I built a matrix directly from x1 and x2 without normalizing them, that matrix wouldn't satisfy the orthogonality requirement. That Q transpose times Q equals the identity. Once I normalize them to unit length, though, they do satisfy this property. That's the key distinction. At this point, to actually prove this main result, that any real symmetric matrix is orthogonally diagonalizable, I need to cover some background on complex matrices first. We'll do that next, and then come back and prove that every real symmetric matrix is indeed orthogonally diagonalizable. Let's do a quick summary before ending this lecture. What we covered here, we stated the spectral theorem, which tells us that if you have a real symmetric matrix, you can orthogonally diagonalize it, and the resulting diagonal matrix will contain only real entries corresponding to the eigenvalues of the matrix. These are the two key facts that follow from the spectral theorem. The important context here is that we're specifically talking about real symmetric matrices. The spectral theorem guarantees diagonalizability for this class. But not every real matrix is diagonalizable in general. There can be real matrices that fail to be diagonalizable, and we saw an example of that in this lecture. Most importantly, we worked through a concrete example using a simple 2x2 matrix and orthogonally diagonalized it, calculating its eigenvalues and corresponding eigenvectors, and then normalizing those eigenvectors. This gave us a set of orthogonal eigenvectors, which we then used to construct the eigendecomposition of the matrix, effectively demonstrating that this matrix is orthogonally diagonalizable. In the lectures that follow, we'll move to the more general case of complex matrices, where the natural generalization of a real symmetric matrix is called a Hermitian matrix. We'll show that every Hermitian matrix is diagonalizable, and this more general result will directly imply the spectral theorem for the real symmetric case, since real symmetric matrices are simply a special case of Hermitian matrices. Suppose you're given a set of data points x1, y1, x2, y2, and so on through xn, yn. You want to find a second-degree polynomial, that is, a quadratic, that best fits this data. In general, for higher-degree polynomials, this same approach extends naturally, but let's focus on the quadratic case here. We want to find a polynomial of the form y equals a plus b times x plus c times x squared, where a, b, and c are the unknown coefficients we're solving for. To find the best fitting curve, we set up a least squares problem. The idea is to choose a, b, and c so that the total squared error between the predicted values and the actual data values is as small as possible across all the given points. This leads to a linear system of equations, often called the normal equations. If you write out the problem in matrix form, you get a system that looks like this: a matrix built from the sums of powers of the x values multiplied by the vector of unknown coefficients a, b, and c, equals a vector built from sums involving the x and y values together. Specifically, the matrix on the left has 3 rows and 3 columns. The first row contains the number of data points, n, the sum of all the x values, and the sum of all the x squared values. The second row contains the sum of the x values, the sum of the x squared values, and the sum of the x cubed values. The third row contains the sum of the x squared values, the sum of the x cubed values, and the sum of the x to the 4th power values. This matrix, multiplied by the column vector containing A, B, and C, is set equal to a right-hand side vector. That vector contains the sum of all the y values, the sum of x times y across all the data points, and the sum of x squared times y across all the data points. Once you've computed all of these sums directly from your data, the sums of x squared, x cubed, and x to the fourth power, along with the sums of y, x times y, and x squared times y. You plug them into this 3x3 system and solve for A, B, and C using standard techniques such as Gaussian elimination or matrix inversion. Once you've solved for the coefficients A, B, and C, you can write down the fitted quadratic polynomial y equals A plus B times x plus C times x squared. This is the best fitting second-degree curve in the least squares sense for your original data points. If you'd like, I can redo this with the actual numerical data from your original video. If you can share a cleaner transcript, the exact data points, or the video itself, I'll be glad to work through the specific numbers and give you the exact fitted polynomial for the particular data set. Let's start with finding the eigenvalues of a matrix. Suppose you have some square matrix A. To find its eigenvalues, you set up the equation. The determinant of a minus lambda times the identity matrix equals 0. This is called the characteristic equation. For a 2x2 matrix, this determinant works out to a quadratic equation in lambda. Solving that quadratic gives you two eigenvalues. Call them lambda 1 and lambda 2. These might turn out to be positive, negative, equal to each other, or even complex numbers, depending on the specific matrix you're working with. Once you have the eigenvalues, the next step is to find the eigenvectors corresponding to each one. For a given eigenvalue, say lambda 1, you substitute it back into the equation. The quantity, a minus lambda 1 times the identity, multiplied by some vector, x, equals 0. Solving this system tells you the direction of the eigenvector associated with lambda 1. Any non-zero vector satisfying this equation is a valid eigenvector for that eigenvalue. You repeat this process for lambda 2 to find its corresponding eigenvector. It often helps to parameterize the solution using a free variable. For instance, if the eigenvector equation reduces to a relationship like one component equals some constant, k, times the other component, then you can pick any value of k to generate a valid eigenvector along that direction. Every choice of k just gives you a different scalar multiple of the same underlying eigenvector direction. Now, here's the geometric intuition behind all of this. When you apply the matrix to a vector that happens to be an eigenvector, or any scalar multiple of an eigenvector, the matrix doesn't rotate or change the direction of that vector at all. It only stretches or shrinks it, scaling it by the corresponding eigenvalue. So, if u is an eigenvector and w is some scalar multiple of u, then applying it to w gives you back a vector still pointing in the exact same direction as w, just scaled in length by the eigenvalue. This is fundamentally different from what happens to a general, arbitrary vector, v, that isn't aligned with any eigenvector. When you apply to such a vector, it typically doesn't just get scaled. It also gets rotated, or its direction changes in some more complicated way, because it's really a combination of the different eigenvector directions, each being scaled differently by its own eigenvalue. This is really the heart of why eigenvalues and eigenvectors matter geometrically. Eigenvectors reveal the special directions in space where a linear transformation acts in the simplest possible way, just stretching or shrinking without any rotation. Any other vector, unless it happens to lie exactly along one of these special directions, will generally experience some rotation or distortion in addition to any stretching when the transformation is applied to it. If you'd like, I can redo this with the actual numerical example from your original video. If you can share a cleaner transcript, the exact matrix used, or the video itself, I'll be glad to work through the specific numbers and walk through that particular example faithfully.